that is an electric skateboard. Well, I might be stretching the definition of skateboard a little bit. Call it whatever you want. The point is, that's being powered by an electric motor that I built from scratch.
You might recognize this electric skateboard. I've made a couple of videos about it before. It's been an ongoing project for a couple of years or so. But up until now, it was always powered by an off-the-shelf electric motor and an off-the-shelf electronic speed controller, which have now been replaced by a custom-made electric motor and a custom-made speed controller. And so in today's video, we're going to take a look at how we got here. Making an electric motor is not that hard, as in making a science project electric motor for kids at school that rotates is not that hard. But making an electric motor that is actually good enough so that you can use it to power a machine or drive a vehicle of some sort, that's pretty difficult. And that was my goal when I started building this electric motor a while back, and I also mentioned that in the original video, was to be able to power something with this motor. And of course we all secretly knew that that would have to be some kind of vehicle. You know, that's just the coolest way to test if your electric motor works. So I quickly realized that the most suitable vehicle to put this homemade motor on would be that off-road skateboard that I had. For a couple of reasons. Some of these reasons were technical, like the skateboard allows for me to very easily mount different sizes and shapes of electric motors. There is plenty of space, it's easy to mount, it's got a good gear ratio, so the gear ratio from the motor to the wheels is 18 times, so that means if the motor spins 18 times, the wheels spin once, so it's a pretty aggressive low gear ratio. So even if the motor doesn't produce tons of torque, it's multiplied by 18 times at the rear wheel, so hopefully even if you don't have that much torque, which could be the case with a DIY motor, you can still get the thing going and get it to move. But also I did it because I thought it would be very cool, because this skateboard is probably the most built from scratch thing that I've ever made. Pretty much the only parts of it that I didn't build were the electric motor and the speed controller, and I guess the battery. And maybe the wheels, and I didn't grow the trees that the wood that the deck is made of came from, but I guess in that way you can't ever make anything from scratch. But the thing is, this is the most built from scratch thing I ever made, except for the motor and the speed controller. So I thought, how cool would it be to also replace those with homemade parts? And that's what I've done now. So the last video that I made about the DIY electric motor project was about the driver board that I was building for the motor, because to use a motor like this you need an electronic driver, and so that's what I was making. And when I made this video, the board wasn't fully assembled yet, so I couldn't show you that it actually worked, but we did talk about all the electronic circuitry, in detail. So if you want to know all the details on how this electronic driver works, I recommend you watch that video. But for now, let's just start with a very basic brief recap of what this driver board is actually for. So the type of electric motor that I've built is called a switched reluctance motor, or SRM for short, and the way that it's built up is kind of like this. So on the outside there is the stator, which in this case has 12 coils on it, and those 12 coils are grouped up into sets of 4 coils each, and those are called the phases of the motor. And so when you energize a phase, that essentially means you energize a set of 4 coils on the stator. In the center of that is a rotor, which is basically just a block of steel shaped kind of like a tooth gear, with 8 teeth on it. So what happens is, when you energize a phase or a group of 4 coils on this stator, the steel rotor will align itself with those coils and therefore rotate. And then you switch on the next phase or the next set of coils so that the rotor moves one step further, and if you keep doing that, then you have a motor that keeps on going. Now, as you can imagine, if you just keep stepping through the phases like this at a constant rate, it becomes kind of like a stepper motor, and so the movement is very, very choppy, and it's unsuitable to use as a drive motor for a vehicle. So what you do instead is something called closed loop control, which means that the angle or the position of the rotor is being monitored. In this case, we're doing that using an encoder that's fitted to the back of the motor. That encoder then sends that angle information to the driver board, and the driver board decides which phase it needs to energize based on the angle of the rotor. So it always switches to the next phase at exactly the right moment to keep the motor turning smoothly. So in a nutshell, what the driver board does is it monitors the angle of the rotor using that encoder, and then based on that information it turns on the correct phase. Also, using PWM or pulse width modulation, it controls how much power actually goes to the motor, so that is your throttle control. Now, to do this switching, it uses, obviously, MOSFETs are the most suitable device, the most suitable electronic component for doing this. So we're using a whole bunch of MOSFETs and a whole bunch of diodes. Again, if you want to know more details about the arrangement, that is in the previous video. And also, I will post a schematic of this driver board online. But we're using a whole bunch of MOSFETs and diodes for this switching, and those components can get quite hot. So what I've done is I've mounted them on the bottom of the PCB, so that if the PCB is mounted onto an aluminium plate, which will also be the back of the housing for this driver board, that plate acts as a heatsink for cooling these devices. Notice how there is a thermal pad sitting on this aluminium, which makes sure that the devices don't make electrical contact with the housing, which would cause a massive short circuit and destroy the whole thing within milliseconds. So once I had this driver board fully assembled and mounted it onto my aluminium cooling plate, I could start uploading some control software onto the microcontroller. And I started with a super simple program that basically does exactly what I just explained. I turned on the motor and it performed horribly. It could not get up to a very high speed, maybe 400 RPM or so was the highest it would go. It would consume lots of power, become very hot, make a lot of terrible noise, so clearly something was wrong. And actually that was expected, because this is something that I'd already experienced before when I tried the motor on my old driver as well. The problem here is that this software doesn't take into account the inductance of the motor. So the problem is that the windings of the motor, the coils, they have inductance. And so when you turn a phase on, it actually takes a little bit of time for the electric current to build up. And also when you turn a phase off, it takes a little bit of time for the current to go back down to zero. Now that can be a big problem, because if the motor is spinning at a high speed, that sort of time delay can become quite significant. And this becomes most apparent when it comes to turning a phase off. So let's say you have one phase energized and your rotor is moving towards aligning with that phase, and when it is perfectly aligned, you want to turn that phase off and move to the next one. So you're going to turn it off just like that, but because of the inductance, the current actually keeps going for a little while after that, which means the phase remains energized. And at that point, because the rotor is moving away from it, it's kind of pulling back on the rotor, it's holding it back, you're braking, and that obviously ruins performance. So it's very important that as the motor speeds up, you have to take this into account. And so you need to advance your firing angles as the motor speeds up. So what I did next is I made another super simple program that does this. And what this did was essentially it calculated, or it counted the number of processor cycles that it took for the rotor to complete one rotation. And it linearly mapped that to a timing advance. So basically, the fewer processor cycles it takes for one rotation, the faster the motor is spinning, the bigger the timing advance. Perfect. And when I loaded this onto the controller, it worked really well, or at least it seemed to work really well. When I was running the motor on the table with no load, it could now spin up to much higher speeds. Then I put the motor on my homemade dyno, and the results were completely different. The performance was terrible the higher the speed of the motor became. It consumed lots of power, it became very hot, it made terrible noise, and so I realized this was not the way. And then I saw that this curve that I made, or rather this straight line that I made, doesn't make any sense. Because if you are mapping the speed of the motor versus the timing advance, then it's a linear map, right? Then it's a line, because if you have double the speed, you need double the timing advance. That makes sense. But I didn't use speed, I used the number of cycles to complete one rotation. In other words, period time, 1 over the speed. And so in this case, that straight line doesn't work, because if you are running at some speed, which means you have some number of cycles, if you double that speed, meaning you get half the number of cycles, you want to also double the timing advance, and each time you half the number of cycles, you want to double the timing advance, so the curve should look more like this. So at this point, I considered theoretically calculating the timing advance based on the speed of the motor, which is possible because I know the inductance of the motor windings. It varied between 2 millihenries in the unaligned position and about 8.5 millihenries when in the fully aligned position. And using those numbers, it's theoretically possible to calculate the timing values. But in practice, it would probably not give me very good results, because there are unknown factors here that can mess with this. And these are things like the possible delay of my encoder, because this encoder is not optimized for high-speed applications. It's more designed to make like little potentiometers and stuff, like knobs that humans can turn. So it's not designed for a motor that spins at 3000 RPM, which means there's probably significant delays introduced by the encoder that I'm using. There is the sampling time of the analog to digital converter on the Arduino, which is pretty slow. Then there is the processing delay on the Arduino itself, which again is pretty slow. And so all of these things also matter, also have an effect, not just the inductance of the motor. And so a theoretical calculation would probably be off, and then I would have to go in and do trial and error to correct it anyway. So I decided to just go with trial and error from the very start. So what I did is I put a piece of software on the microcontroller that would allow me to change the timing manually. So I could just type in a value on my laptop, send it to the thing, and then it would set the timing to that value. And then I ran the motor on the dyno with some load applied to it, and I would, through trial and error, try to find the timing value that gives me best performance for that particular speed. And I repeated that a bunch of times for various speeds, and so now I had a table with speed in one column and optimal timing value in the other. Then I put those into a spreadsheet editor so that I could plot a function that would match these points as closely as possible, and theoretically speaking, that function calculates the ideal timing value based on the speed of the motor, or the number of cycles which we're still using. So the thing is, because we're using a pretty slow microcontroller, a little Arduino Nano, it's not a good idea to run this function in real time while the motor is spinning, because that would take too long on this processor, because it's floating point operations, which it really sucks at. So what I decided to do instead is build a lookup table. So when you power up the device, it starts to run this equation 500 times for 500 different values, and builds a lookup table which it stores in memory. And then when the motor is running, it just has to retrieve the right value from the table, so it doesn't have to do the maths on the fly, which helps a lot with minimizing the number of CPU instructions required. With this new software, the motor performed a lot better, particularly at higher speeds. But I did notice that when running it for extended periods of time, the windings would get quite hot. So I disassembled the motor again, and I glued some small cooling fins onto the rotor in an attempt to force a bit of airflow through the machine as it rotates. And this did seem to help a bit. The windings got less hot, at least when running at the same load and the same speed. Even though the airflow isn't that powerful, because the motor is not spinning at a very high speed, at least it wasn't on the dyno for sure, it does help a little bit, and it doesn't hurt to put these things on there, so I think that was a good upgrade. So with all of that done, I think a lot of you are wondering if I did any measurements with that homemade dyno of the torque of the motor, because that's kind of what I built it for, measuring the torque. Now, I know that some of you didn't really trust the accuracy of this DIY dynamometer, and to be completely honest with you, neither did I. So what I decided to do is take some measurements with the dyno and then find another way of trying to confirm those values. So when I measured the torque on the homemade dyno, the peak torque that I measured was about 0.6 Newton meters. So that is the absolute maximum torque that it was able to produce for, I guess, 10 seconds or so before I was scared to burn up the windings and turn it off again. The continuous torque that it was able to sustain for longer periods of time appeared to be between 0.1 and 0.15-ish Newton meters. So those values are not spectacularly high, but they're certainly also not bad for a homemade electric motor of this size. You know, they were certainly a lot better than anything I've ever built before. Then what I did is I built this setup. So in this case, the motor was essentially pushing down directly onto a scale. The disadvantage obviously being that the motor is blocked, so we cannot measure the running torque of the machine, just the stall torque. But the good thing about this setup is that it's so incredibly simple that we can probably trust its results to be pretty accurate. And with this setup, I measured that the stall torque of the motor, the maximum stall torque again that I was able to, or willing to do for 10 seconds before I got scared of burning up the windings, was about 1 Newton meter, so significantly higher than what I measured on the dynamometer. And the continuous torque, if we assume that the ratio between this test and the dyno test is roughly constant, in that case the running torque, the continuous running torque of the motor should be around 0.2 to 0.3-ish Newton meters. So again, not too bad for a homemade electric motor of this size. Having done these tests, I estimated that these numbers should be good enough to put the electric motor on the skateboard and be able to ride it. So I decided to go ahead and put the motor onto the skateboard, which was super easy because I had made this motor to have the mounting holes in the same location as the motor that I previously used on this skateboard, so it was pretty much a drop-in replacement. Now for the driver board, I of course had to make the rest of the housing, which is just made out of a sheet of aluminium, and I put this D-sub-9 port on it to connect the throttle and the encoder, because this is a nice compact port. Perhaps I should have used something like waterproof or made for outdoor use, whatever. I thought this one was okay. Now initially I wanted to put this driver board underneath the deck of the skateboard near the battery where the old driver, like the old speed control, used to be as well. But unfortunately my new driver unit was quite a bit bigger than the old one, because it didn't use surface mount components. So I didn't have enough space there, so I ended up putting the driver board just right on top of the deck, right in front of the electric motor. So now I guess all the equipment is out there to see. But I ended up kind of liking it, because now you can see all the equipment, you can see what all the effort has gone into. In hindsight, it would have been a shame if it was underneath the deck and you couldn't see it, so I kind of like it this way. So now I could actually do a little first test ride, so I did, in the backyard, and it actually worked. It moved for the first time with the homemade electric motor, which was really cool. But I thought I could make it just a little bit better still, because it wasn't all that powerful, it wasn't all that fast, and it got pretty hot after going back and forth a bunch of times. So I did one more thing, which is that I took the motor off again, took it apart, And then I tried to make the air gap smaller, because the air gap size in my motor was pretty big. I think it might have been like a millimeter or something at the end of the day. And so I tried to fix this by sticking some super thin strips of steel onto the rotor in an attempt to further lower the air gap size and increase the torque output. And so I did this, put the motor back together and tried it again, and it seemed to be just a tiny little bit better. Not a huge amount. I don't know if it made such a big difference in the end. I couldn't make the air gap super small anyway, because the manufacturing tolerances of my DIY front and back plates weren't good enough. So maybe the metal strips that I added helped a bit. They didn't help all that much, but I was happy that the skateboard at the very least did actually work. And so that is where we are now, where I can show you this actual test footage from me riding the electric skateboard in the woods. So let's see if we could just do some slight off-roading and go into this. Just going to handle going into a little bit of soil and grass. Oh, okay, so just rode into a ditch there. I'm just going to pull back a little bit. So, as you can tell, it's not a very optimal skateboard for heavy off-road use, but it will handle probably, a little bit of super mild off-roading. Let's try this. There we go. We'll go through a little bit of sand. That's no problem. It's struggling though. Now, I have to admit that the performance isn't great. It really struggles when you go up a slight hill or when you go off-road. But the fact that it moves at all, I think, is a big win. And I'm actually planning maybe to build another version of this electric motor to see if we can make something that is actually capable of going up steep gradients and going off-road and stuff like that. For now, though, I'm quite pleased with the result. But then at some point, while I was testing my skateboard, this happened. So something went wrong, which is that the motor is just completely blocked. It doesn't rotate anymore. See this? So what I think has happened is, I think one of the super thin slices of metal that I attached to the rotor came loose and got caught up between the rotor and the stator, and now the whole thing is just jammed up. So yeah, I can't fix that right here in the woods. I have to take apart the entire motor. So I guess I'm done filming for today. Now luckily, I'd already recorded pretty much all of the test footage that I wanted, so I can still go home and edit this video, which of course you are watching right now, so that means it was still kind of a success, I guess. So if you enjoyed this video, then maybe consider clicking the like button and perhaps even subscribing to this channel. And of course, all that's left for me to say is thank you very much for watching.